follow the Fourier transform business. So the 2D Fourier transform business, that's now in the Fourier analysis chapter of PMFM. So you have that on the website, and also the MRI business is also on the website. So that's not, so you don't depend on the Google Drive folder for that, because it's all on the PMFM website. So the material, yeah. Good. So then today, the final 2 sessions in neurocognitive methods and statistical methods in this term that I will run. So we start with magnetic resonance imaging, and then later on we do PPI and finish on PPI. So the aim for MRI then today is to now basically bring all the stuff that we discussed after Christmas and a little bit before Christmas with differential equations together and understand one of the fundamental things in magnetic resonance imaging, namely sequence design. So programming the MR computer to turn on the gradients, excitation pulses, and so on in such a way that in the end you get an image. And of course, there are many different sequences that you can run on MRI scanners. And what I will introduce is a fairly basic 2D Fourier transform based sequence. And of course, the reason why I'm doing this is because that's fairly close to the echoplanar imaging and gradient echo image sequences that are actually used for fMRI. They are not quite that, because there are some additional concepts that one needs to introduce them, but on the other hand, they really build on the sequence type that I'm discussing today. So if you want to understand more advanced sequences, which are not really that much more advanced, but a little bit more advanced, like gradient echo sequences or echoplanar image sequences, you have to understand the 2D Fourier transform based sequence first, because these other sequences build on that. The whole thing is also based on a MATLAB simulation, so the code is of course also online. So if you're happy with some basic MATLAB, you can of course go much deeper into all of this by looking at the simulation itself. And might, depending on how things go, maybe we also look at the code, but I was going back and forth, and this morning I decided I think I want to do most of the stuff without the code. Good. So where do we start from? We start from the MR signal equation again. So remember that the MR signal is a time-dependent signal. So the scanner measures a signal over time. Yeah, it's a time series that we're dealing with, like most of the, like all of the interesting signals in cognitive neuroscience, e.g. fMRI, reaction times. They are all, reaction times not really, but the interesting signals are all time series. So the MR signal is a signal that is acquired over time. As we discussed now repeatedly, it's a complex number that is acquired at each time point, and as we also discussed repeatedly, a complex number means nothing but that it's a two-dimensional signal, so that you can isolate the real part and the complex part, and then look at the real part and the complex part individually. And so you might always read that this is a complex number, not as that it's something complex and hard to understand, but that it's essentially a two-dimensional signal. So at each time point you get two numbers, a real number and an imaginary number instead of one number. And then, of course, we, that's still wrong in there. it's a signal that is acquired for each time point, and what we've seen also then is that this signal that is acquired is a double integral, because we are talking about the signal that is acquired from an excited slice. Yeah? So what you always should keep in mind is that what we are talking about here, and in general, when one talks about 2D Fourier transform based sequences like echoplanar imaging or gradient imaging, is that if this is the entire sample in 3D, so that's what you're trying to measure, then there has been a Z gradient that determines the processing frequency in the Z direction. So Z is in this thing, so I'm thinking about somebody lying in the scanner. That's the Z direction. There's a Z gradient, so the magnetic field depends on the Z location, and then the excitation pulse, which we haven't covered in any detail here, is tuned in its frequency to the place or Z-dependent lambda frequency, and excites one slice in this sample, so in the 3D sample, something like this. And the slice and the signal that is then acquired refers to the spatial integral over this slice. So that's the thing that we have did like 2 sessions back or so, that it's the average signal over the slice, which you can see as either it's a very thin slice, so there's not much to average out, or you can see it in the way that it's a very thick slice, and it's essentially doing an average over the Z dimension. Yeah, but that's the reason why we only consider the X and Y coordinates, because we assume that this is a representation of region in space that we know, because we know how we excited the slice. Yeah. So remember that MRI images are the typical EPI images are quite slice-wise. So you have these 3D volumes which are made of, let's say, 32 slices, and these result from exciting the slice in a specific region of Z space. So we are looking, so our time point 0, that's these are 2 important things that you that are behind all of this, which are not explicit, not always then made always again and again explicit. So time point 0 is the excitation pulse, and Z coordinate known from excitation. Yeah. So this should be completely clear, and the problem that is then still to solve is how to now create an image of this slice in 3D space, this XY slice in 3D space. And to this end, we discussed that we form this double integral over the magnetization, or I also call it now image function sometimes, so I go back and forth calling it magnetization, initial condition, and image function, because it's all the same thing. It refers to that in this slice, so which is now seen from the top, x, let's do it this way around, y and x. There is in this slice average over space, so in this spatial average over the Z direction, there is some variation in the magnetization. Yeah, and last time we discussed that, for example, you have this kind of variation in magnetization. So where it's dark, it's, let's say, high, and where it's white, it's low. Of course, what we always have in mind is that there's kind of, I don't know, a brain that looks, I don't know, something like this. it's a little small, but yeah, so that there is some variation in the magnetization that is induced by the strong magnetic field, so that conforms to such a function. Yeah, yeah, that's a variation in proton density. That's the image function. That's the net magnetization, the magnetization function. It's all the same thing. Important thing is this is how much at each location in space, indexed by xy, at equilibrium, how long the magnetization vector is. Yeah? And then remember, at excitation, that magnetization vector is tilted into the transverse plane, and this is the initial condition for our precessing movement of the magnetic moment vector, and this is this value here. Yeah, so this should also be clear. And then we've seen that the MR signal equation has as its second factor this thing here. Which describes, maybe it's, which describes two things at the same time. Just finish this here, and that's the image function or net magnetization. And the second factor, so this complex exponential, describes a space-dependent rotation of the transverse magnetization. And this is what we discussed, of course, all the time in the beginning, so shortly after Christmas, where we looked at the overall 3D magnetic moment, which does this in 3D, this thing that it rotates and builds back into the z-axis with some decay. We then abolish the decay for the purpose of the signal equations. That we assume that the decay is either fairly long or that we acquire the data fairly early after excitation, so that we can get rid of the decay. And we also removed from this equation this omega 0 dependent rotary movement that is happening independently of the spatial coordinates. So we are left with this space-dependent rotation of the transverse magnetization. And we've also seen then last time that this equation can also be interpreted as the 2D Fourier transform of the image function, and that then from this interpretation, this exponential, this complex exponential refers to a spatial filter function that we also looked at last time in more detail with the combination of this sine and cosine function in 2 parameters. Yeah.
I was just wondering what I was a bit confused with the indices of like the MC of XY, and then you have MC, like the tiny CSD index. What, like, is that the same thing as that MXY?
It's not quite. It's the difference is that thought this is also written up somewhere. Yeah. So if you look into equation 4130, sorry. Do you see that?
Yeah.
So there on the right-hand side you have the MC, and on the left-hand side you have the MXY. And the difference is that the MC is the magnetization depending on, so the complex form of the magnetization, so the initial condition depending on X, Y, and Z. And the M is then the integrated version of this over the Z domain. Yeah, so you can so you can also view that as, so there are two ways. Either you view that as the average over Z, or you say, well, this average, so this delta Z is really, really small, so essentially it's just a slice. In the, I mean, it's always just a slice, but you either see it as a really two-dimensional entity, or you see it as an average over some extension in Z. But that's the connection, yeah?
And that in 4130, that MC is the same MC than in the 4122, where we have MC of R.
Exactly.
Because it's space, and that's X, Y, and Z.
Yes.
Okay.
Yeah.
Thank you.
Exactly. So that's the beauty of hierarchically building up things, so that things later on relate to things early on. Which can, of course, always go wrong, but I try to make an effort. Okay, yeah, so that's the image function exactly, and yeah, so we interpreted the whole thing as the 2D Fourier transform of this mxy. Good. So now I want to, no, we are not quite done. So one thing that is, of course, also important is what these kx, t, and y are. And they are, as we also introduced, they are the time integrals of the gradient waveforms. Oops, that's wrong. This should be a tau. And then they are standardized by this gamma divided by 2 pi. So the important thing is that from the perspective of the Fourier transform, 2D Fourier transform, these are the parameters of the basis functions, so like the frequencies of the generalized cosine and sine functions in the one-dimensional case. And from the perspective of the MR imaging process, these are things that we can actually manipulate, because we can turn on and turn off these gradients during the image data acquisition process. And the essential thing about a sequence then is the question of when certain gradients are turned on and turned off, and when data is acquired. Yeah? But so this links already the Fourier transform parameters. Remember these sine and so these two-dimensional sine and cosine functions with varying spatial frequency and varying orientation that make these radial patterns that we looked at last week, which kind of looks like this Japanese war flag or whatever that is. And that's the kx and the ky. On the other hand, these are things that can be manipulated by the sequence. And now, yeah, I'm trying to bring these things together. Yeah, good. And yeah, let's start as follows. We look now first at the gradient waveforms. So what we assume is the following. We assume we have some time point 0 and we have some time point corresponding to 200 milliseconds. Here the excitation pulse happens, and the entire magnetization is tilted into the transverse plane. So that's when the whole thing starts. And of course you remember that when things are tilted into the transverse plane, afterwards the net magnetization at each location in space, so in this case xy, starts to precess. It decays, but we are not talking about the decay right now. We are just talking about the precession as described. And yeah, so that's what happens afterwards. Now, the first thing is that we then acquire data at certain time points. So here I'm plotting 5 time points starting, I think, at 1000 milliseconds. So these are time points, something like this. We don't need this actually. You see it down there. These are time points at which MR signal is acquired. So we then have the MR signals STN, and we have 5 of these complex numbers. Yeah, what's the question?
Well, we were just not sure, excuse me, in case you have noticed that you are not recording, it appears like because of the... Oh, it is, okay.
Is it? Yeah, it's recording. Okay. Thanks. Are you actually watching these videos?
Yes.
Good. Okay, so keep this in mind. This is 2 seconds, and what happens is excitation pulse comes. Of course, excitation pulse for a specific slice in the Z direction. Yeah. So excitation pulse comes, and at some point later, data points are measured, and we get MR signal at these 5 data points. Now, what also happens is that we deal with 2 gradients. One being, for the purpose of the initial example, the Y gradient, and we keep, for this example right now, the GY at 0. Yeah, so keep in mind that GY is a function, that's a gradient waveform that maps time to some gradient amplitude, and here GY t is defined as 0 all the time. Yeah, so you see that it just remains 0. So we will also do something with GY in a second, but not right now. What we also deal with is an X gradient, and this X gradient we actually turn on in this example. We first leave it at 0 for t smaller than 1000 milliseconds, and then we set it to some positive number. So just making something up here. I think that's what I have in the simulation. It's then set to some positive number. So in this kind of boxcar manner, yeah. And at 2000 milliseconds, the whole thing is over, and the next excitation pulse would come. Yeah, so the thing is really over here. So that's it's kind of the first sequence example that you get to know. So the Y gradient doesn't do anything. The X gradient is turned on at 1000 milliseconds and then stays on until the last data point is acquired, and then the whole thing is over and the next excitation pulse comes. What we have to talk about are the time integrals of these functions. So the integral from 0 to t of gy and the integral from 0 to t of gx. So if I plot the integral of gy over time, so as a function of the upper integral boundary, what do I get in this example for gy? So again, what is an integral in terms of a definite integral?
0.
It's 0 because in this case so it's the area between the function and the x-axis, and right now the gy stays at 0 all the time, so the area is also 0. So I'm plotting this here next to 0, so it's not changing. So that's this. Now, what about the gradient of the integral of the x gradient as a function of time? Any suggestions? So first of all, what's the integral if I look at the integral of gx at this time point here? What do I have to fill with red to say this is the integral?
All left of it.
All left of it. So this, right? Yeah. Good. And now assume that I plot this for each point in time. So at this point in time, I plot this area. At this point in time, I plot then these things. And at this point in time, I plot all of these things. So what do I get if I plot that? Constant if I plot it as a function of time. So here's the this is the argument that so at
it's always the same.
yeah, but think about it. So for this time point t1, I plot this area. For this time point t2, I plot always going from 0 to the current time point. Yeah. So in this case, it's actually a linear function, not a linear fine function because it stays at 0. But the important thing is that it's increasing. Yeah. So that's to make this clear again. So that's I think the best way, or at least one way to write this, is like this. The important thing is that this is a function of t. Yeah, so the upper integral boundary is always going up. If you plot this as a function of time, of course, until the x gradient is turned on, nothing happens. So the integral is always at 0. But once the gradient is turned on, it's just a linear increase in the integral. If you ever did drift diffusion model and MT representing the movement to the left versus the movement to the right, and then you have some integrative process that looks at these populations, that's exactly the same idea. Don't know, did you do drift diffusion model and MT and orientation tuning or something like this? No. Yes? Some did, some did not. But that's the same idea. So the representation of some motion is then constant, and there's an integrator looking at that, and this increases. Of course, with a drift diffusion model in cognitive neuroscience, you will not understand this because, anyway. Okay, so that's these are two things that are important. And what is also important is that these time integrals, they refer to our Fourier parameter. Yeah, so the y integral is ky, and the x integral is kx as a function of time. So one important thing, of course, here is that when the MR signal is acquired, so at these black dots, the time integral and hence this Fourier parameter kxt is different, right? So it's at the first black dot it's 0, then it's here, then it's here, then it's here, and then it's here. Yeah, so the Fourier parameter changes with time because the gradient is turned on, and the time integral of the gradient refers to the Fourier parameter. Yeah. So maybe a little bit nicer. This is shown here. Oops. Although it's actually the same. So this is our y gradient waveform in blue. Its time integral in this example is 0, and then in for x you have this waveform, and it's this time integral here, and then you have the time points of when data is acquired. Yeah, so that's and at 0 there's the excitation. At 2000 the whole excitation experiment is over. Good. Keep this in mind, yeah, because we are going to something different now, but we will come back to this. So that's the, if you want, that's already the one sequence part 1. Whatever. So the other thing that we have to look at is now first we have to look at our image function. Yeah. So these mxy, these are two-dimensional entities, so complex numbers that we can represent as arrows, and then the important thing is that first of all they so one thing is important is that they are phase aligned at time 0. That's one thing that we assume, which is induced by the excitation pulse, phase aligned at t equals 0. What else? And yeah, magnitude dependent on xy. Now we're looking at space. So here's now x and here's now y. And we have these magnetizations. The thing is, this is now a function of xy, and what we are doing is we discretize this function, so we assume that we look at a discrete number of points in the x direction, so I use 2 to the power of 4, so that's 16 points in the x direction and 16 points in the y direction. Yeah, so we're looking in terms of the xy coordinates, we're looking at 16 points in the x and 16 points in the y direction. So yeah, I don't want to do 16, so I'm yeah 16. Why 16? I will show you in a second why 16, because it fits the plot. So, but it and it looks good. So something like this at these locations. So I stop in a second. But at these locations, these are the xy coordinates. Yeah. So this is here, for example, that's xi and yi for I don't know I. Whatever, yeah. So it's these are the locations. So these are the xy. But at these xy, you have two-dimensional entities, which are which you can plot as arrows, which are of course the things that we looked at from in 2 ways. So we saw this first in this lecture like this, where we had the z, and we started, okay, we tilt this into the xy plane, and then it starts rotating, yeah? So we've seen this, and we also said we are only looking at what's happening actually in the xy plane, and now we are actually only looking at what's happening in the xy plane. So we just saw something like this, and then it started here and rotated. And what we said is we look only at the xy plane. We are now looking only at the xy plane, and we forget about the decay. Yeah? So nothing is decaying right now. Yeah? So forget about the decay. The thing is just rotating. But this was always only one. Yeah, this was only one of those at one location xy. Now we're looking at this whole thing as a function of xy. So we have lots of these arrows. Yeah. And the dependency on xy actually means that that both the length and the orientation of these arrows, both the length and the orientation of these arrows can change. We assume that at time 0 they are all in phase, so they are all pointing in the same direction, but they can be of different amplitudes. Yeah. So remember that we, again from your little knowledge, there is this equilibrium vector. The magnitude of it can change, but at equilibrium it's pointing into the z direction, and then it's tilted into the xy plane. The magnitude can vary. The fact that it's pointing into the z direction and at moment of excitation is located in the transverse plane does not change. So so there are some arrows which have a longer magnitude. So let's say drawing some of longer magnitude in here, so they would look like this. And then there are some that that are relatively short. So the problem is if you plot in arrows of longer magnitude into this, it gets a little bit hard to see. So what I'm doing in the MATLAB simulation, instead of encoding the length of these vectors in their actual length, I encode that in their color. Yeah, so the lightness of their color represents their length, and this is just because it's a little bit hard to see if you put in very long arrows somewhere. So what I've just drawn here, I've also drawn nicely here, and that's why I chose 16, because it covers the thing quite nicely. So what you see is here the net magnetization as a function of x and y, tilted into the transverse plane and being of different and space-dependent magnitude, where the magnitude is encoded in the color. Yeah, so basically all these dark arrows, there the net magnetization is low, and in the middle you have this circle where the net magnetization is high. Yeah. So the big step conceptually you have to make is that when we looked at the arrows previously and the rotation, there was only one at one location, and now we're looking at these over many locations. Yeah, happy with that?
And what this lens depends on? What this lens depends on?
This lens here? Okay, that's a good question. So that's the proton density. That's depends on how many, that's the net magnetization in a given area. That depends on how many protons there are. You can also view this differently. You can also say, if we're not going to discuss this in detail, but this could also represent differences in T2 time constant, but or a difference in T1 T2 constant. The important thing is that something in this net magnetization properties over space varies, and what I'm using here is just the net magnetization itself, which is known as proton density. Yeah.
So if those different points are now representing different locations of x and y, what were the different values for x and y then representing before the graph that we looked before? For example, in figure 41.3, there we also have those planes of the.
Let's have a look. I'm not quite sure which one. Which.
We also have those transverse planes.
This here?
No, two pages after that.
2 pages after that? There's nothing 2 pages after that.
Like Fourier,
this. Yeah, that's in a different. That's actually a good question. It's actually the same. So maybe postpone this question a little bit because we will come back to that. But it's actually the same. So good. So this is now a representation of the net magnetization of the image function or the net magnetization over space and at time 0. Now this was all at time 0. So now well, actually, this is what. Yeah, sorry. This is not at time 0. This is at time 1000. What we assume here is at time 0, things were in phase, and then there was nothing that made the vectors over space get out of phase, because there was no gradient on that induced different precession frequencies over space. Yeah, so basically at time point 0, all of them start to rotate, and then at time point 1000, we take another step. We take a snapshot, and they are still all in phase, and this is what is shown here. You can also view this as being the snapshot here, but that will not be appropriate for the remaining rows of this graph. Now the important thing is that everything is in phase at this time point. All the arrows point in the same direction, but now an x gradient is turned on, and if the x gradient is turned on, what we have from our signal equation is that now, how do we do that best? We have our rotating thing here. And so ky was 0 all the time, kx was also 0, but now kx t is not 0 anymore. So now the frequency of rotation of these arrows depends on space. Yeah, so because here we have this x, and this is now multiplied with a positive number, namely this kxt. And what then happens is that now, as you all remember, the precession, so the rotation frequency is dependent on the magnetic field. And now you can, so you can view it simply as the magnetic field now varies over x space. That means that that depending on the x location, certain magnetic vectors here rotate faster and others rotate slower. Yeah, so they were in phase, and then one of them starts going faster, and one of them maybe slower if it's on the other side of the gradient, so they get out of phase. If you then take a snapshot at one point after this has been happening for some time, you observe that things are out of phase. And one way to view it is that, let's say they rotate in this clockwise order, and then at this point in time that we're looking at here, this is still, no, then it would be, it depends on how you look at it. So they are here. Let's say it's easier if they rotate counterclockwise. So this point, so they rotate this way. Then it's easier to interpret. Otherwise, you would have to go around the circle. So all of these that are at this location in X space, they are in phase because over Y there was nothing happening. But in the X domain, these arrows here are a little bit further already. These are a little bit further, even more, and these are the furthest if they rotate like this. Yeah, so you see that over Y nothing changes, but over X, the ones that have high X coordinates, they are further in their anti-clockwise rotation than the ones at low X values. And the reason for that is that there is a gradient over X. And this is if you want to plot this or quantify that, this is exactly what this equation does. So there's a dependency on X, and this is the integral of how much the gradient has been on. So one way to also view this is to view this whole thing as an angular function that depends on x, y, and t. So the frequency of this two-dimensional thing, so it's a two-dimensional rotating thing, the frequency, or now this is the phase, this is the angle, depends on x, y, and time. Yeah, so this is what you need to build in there. So it depends how fast it rotates, depends on where it's located in x and y space, and to where it has rotated at a given time point. That depends on the kxt factor. Yeah. So this is kind of the this is the accumulated phase difference at this this point here in time, so at the second data acquisition time point. Yeah, and exactly like this, the gradient can stay on for longer. Then this difference in frequency has been happening for longer, so the accumulated phase, so the difference between the orientation of these vectors at a given point in time is increasing. Yeah, so you can see that the difference here is, I don't know, let's say 45 degrees from -1 to +1 in the x domain, and here it's now from -1 to 1, and it gets even stronger. So now coming to your question, because this is now how the rotating magnetic moments behave over time while the x gradient is on. Now what this induces is, of course, a variation in the x and y coordinates of these vectors over space. So a different way to look at this is exactly as what you brought up, namely this picture. of these basis functions when the ky parameter does not change. Yeah, so the ky parameter does not change, but the kx parameter changes. So if you have some fantasy, essentially, but I think it's fairly obvious to see that these kind of vertically oriented pattern of these basis functions, so that you have something high here, that you have something low here, something high here, and something low here. This you can actually see in these patterns. If you look at the upper row and just go over the upper row, you see that if you now imagine pointing down refers to something dark, and pointing upwards refers to something white. You see this pattern of going up and down over X space in this vertical manner in the orientation of these magnetic moments. Yeah, do you see this? Good. Now the final thing is, so this is now, essentially this is not a translation of the idea of these basis functions being vertically aligned with, or being of vertical orientation and varying frequency. The final thing is that the MR signal is then not a snapshot of all of this, but the product of each of these little arrows with with the magnetization that is given by their color. Yeah, so that in the end there's only a single value, which you can. So the easiest way for me to understand this is that you imagine that this is a filter function which is put on top of the magnetization, and if there's some covariation between the filter and the image itself, then you get a high value, and if there's not much covariation, you get a low value. And what has been created here by means of the rotation of the magnetic moment vectors is this line of a spatially oriented and spatial frequency filter. Yeah. Essentially, this is just ky stays 0 and kx increases, and this is then represented, and I we will take a break in a second. This is represented in what is known in MR as k-space as follows. So the kx changes here because this x gradient is turned on when the data is acquired. So these are these 5 data points that are acquired over time here, now represented in terms of their kx and ky coordinates. And as you can see, kx changes, so you have this vertically aligned but varying spatial frequency locations in k-space. Ky does not change because ky is always 0 because the y gradient was not turned on. So if you now basically do this integration over space of multiplying the magnetization size with these how do I explain it? With these 2D vectors that point upwards or downwards, then you acquire data for these points, and these points are plotted where I now have the cursor in the discrete Fourier transform representation here. Da, 1, 2, 3, 4, 1, 2, 3, 4, 5. So these, so there is, and that's a typical thing, there is, the signal is largest if you are usually at the 0 because there's some low frequency component, and then it decreases a little bit. So let's have a break now and then talk about the y gradient. Yeah.